Hello, everyone. Welcome back. This is Ramesh Raskar, Associate Professor at MIT Media Lab. And I'm going to talk about contact tracing and reopening businesses with safe paths. And some of the work I described is also being done by the nonprofit PathCheck. And today I'm going to focus on the role of machine learning as we try to create a global AI that still is privacy preserving for an individual. So SafePaths is a privacy preserving platform, which on the left side, as you can see, is facing the citizens, a SafePaths app that's for exposure notification, contact tracing information, access to resources, and very soon, symptom tracking, quarantine verification, and other validation. And then on the right is a solution for public health and businesses, which is a dashboard that can expedite tracing conversations, improve the quality of data, but very soon can also create dashboards with hotspots and predict the spread. Coordinate population at home, and of course, create solutions for certification. And in that sense, SafePaths is one of the largest open source effort for COVID-19. And we use proximity technologies such as GPS and Bluetooth or Apple, Google, and we'll also support the protocols like PACT from MIT in the future, and other modalities. And we want to achieve all of this without infringing on personal freedom. In that sense, SafePaths has three pillars. The technology pillar, where there's a flagship app, but we're also helping everybody else create their apps as well. Backends and dashboards and web tools. A lot of algorithms we publish on a regular basis, SDKs. And privacy and interoperability are the two main aspects of the technology. Then for the think tank, we are publishing standards, privacy and ethics guidelines. We convene stakeholders. We do landscape analysis. And then implementation, which is kind of last mile efforts, which are mainly conducted by PathCheck, the foundation, are about public health engagements, training, monitoring, bringing solution providers and solution seekers together, such as startups and relationships with corporations for their software deployment. And SafePaths has three broad audiences. For citizens, it's of course the app and the self-assessment and information. And the emphasis for this particular call is about relationship with public health and businesses. So for public health, as I said, we have open source code, and we're helping many jurisdictions deploy their own apps and their own dashboards. And our goal is to really support existing manual contact tracing operations and amplify and simplify their efforts with interoperable backbone. And the SafePaths Alliance, of course, has fantastic MIT faculty, and it's also shaped by conversations with WHO and HHS and partners like Mayo Clinic and EY and so on. And the beauty is that a lot of the APIs that are being released by organizations, including Google and Apple, for, in this case, a Bluetooth API that allows individuals to figure out if they came in proximity of an infected persons, but able to embed many of these APIs, and they're privacy preserving. But if you look at the flow, experience flow for an individual through COVID-19, either an healthy individual or infected or an exposed person, those flows are actually very complex. The exposure notification is just a small part of it, but then there's contact tracing, which is the ability to talk to the person who may have been exposed. There's triaging, there is need to testing or isolation, telehealth, quarantine verification, have you maintained a quarantine, talking to public health who can authorize certain tests or certain certificates, and then also kind of creating a closed loop system for public health. So the challenge is, how can we preserve all of this? How can we achieve all of this while preserving privacy at every stage? And that means without knowing the name, phone number, email address, or some kind of a national ID number, how can we support most of these processes? And it's privacy preserving kind of to avoid a big brother surveillance system. But of course, information is required for any particular entity. But we want to avoid slipping into a big brother scenario. And by doing that, hopefully we can improve the adoption, and without infringing on personal freedom, the population that's marginalized or are fearful of law enforcement, are usually discriminated against, will feel like they can participate in the systems. It's a win-win if you can create a privacy-preserving solution at every stage. So today I'm going to talk about how privacy preserving happens, not just at exposure notification and contact tracing, but also later on, which requires a lot of machine learning tools, as you can imagine. And privacy is a single word that encompasses multiple ideas. It encompasses the notion of consent, regulations like HIPAA, trade secrets that prevents a hospital from working with insurance player versus a pharmaceutical company, and also national security, because a social graph of a country and the health of individuals is also a national secret. And you don't want to centralize that and subject that to a data breach. And at the end of the day, privacy also includes the notion of incentive. How can we encourage healthy young people to participate in the system, because there should be something in it for them as well. And you can have a similar experience flow for businesses as well, whether you need a solution at the entry point of your factories and workplaces, how do employees enter the office, how do you schedule the meetings and stagger them, and so on. And again, we want to achieve all of this in a privacy preserving way. So if you see our website, we are publishing the white papers with a very rapid frequency of how do you add location context with encryption, how can you use Wi-Fi co-location, what are some privacy guidelines, how can you use Bluetooth in a multi-hop analysis, if you use GPS only, is there privacy preserving intersections you can do, techniques like split learning for distributed and private machine learning, if you're writing apps, what could be the unintended consequences, and so on. So I encourage you to look at the website. We are writing the white papers even before they're published. So coming back to machine learning aspect of it, if you want to achieve all these goals, let's say you have a symptom checker, let's say you have a particular questionnaire on your phone, or you have a diagnostic test on the phone, how can you create machine learning models without individuals releasing everything about their own information? And so this problem boils down to creating a distributed and private machine learning solution. So here on the horizontal axis, we have abilities to protect data. And anonymization, as many of you know, is not the same as privacy. And using overlapping data sets, you can actually re-identify the individual. So anonymization, let's consider as the lowest possible way to protect data. The next idea is to obfuscate, which is add some noise using techniques such as differential privacy. And probably the best method to protect data is to encrypt it with techniques such as homomorphic encryption. But the challenge with that is if you start protecting your data, the utility, which is shown on the vertical axis, also goes down. So if you encrypt, then you can also do statistical analysis on your data, but you cannot run inference or train full-fledged machine learning models. And so a few new methods have emerged in the last few years that allow you to train machine learning models without exchanging raw patient data. One is called split learning, and the other one is called federated learning. And the idea behind both these approaches is instead of sharing raw data from the phones or any medical records, how can you share some wisdom, some kind of a collective intelligence or a feature space, and share wisdom without raw data? So let's look at these two approaches very quickly. The first one is federated learning, proposed by Google. It's a fantastic method that takes the data that you have. Think of the clients here as smartphones of the users with COVID, and they can go through symptom checker or questionnaires, and the raw answers never get uploaded to the server, but you train a local machine learning model, and the machine learning model gets better and better and starts sharing just the weights of those machine learning models to the server. And the server can take all these partially trained models and effectively average them at the server, and that becomes a better model than a model at any one of those phones. And this process continues with few cycles, and eventually you get a great model that you want to train. Split learning, which is a technique from our group at MIT Media Lab, uses a slightly different approach, which is still for distributed machine learning, which is you convert each answer from this phone into an intermediate representation, which we call smashed data or smashed knowledge. And only that smashed knowledge is shared with the server. So the server doesn't know anything about the raw data at the client devices, but only knows this intermediate representation. And again, the key idea here is that intermediate representation, the smashed data, does not reveal much about the input. And we think by doing a mathematical analysis of what data gets leaked in those representations, we can give some mathematical guarantees on how these methods could work. So please look at how we reduce the so-called data leakage in techniques such as federated learning or split learning. So the key benefit of techniques like split learning or federated learning is that compared to traditional machine learning methods, first of all, you get great privacy. And second, you can simultaneously reduce the computation and bandwidth loads as well, right? So that's key for techniques like federated and split learning. So in summary, now we have an opportunity to attack COVID-19, not just for contact tracing and for exposure notification, but you can do this for everything else, for triaging, where there may be questionnaires or self-assessment, or for quarantine verification by using sensors on the phone, the video, audio, GPS, all the sensors on the phone, and we can put all of that into a machine learning model to provide better and better services. So this is the kind of work we're doing at MIT Media Lab as time goes on, as we move beyond the contact tracing aspect of it. So if you're a public health or a business entity and thinking about IT solution, we think it's not just enough to create a contact tracing solution or a machine learning solution, but should be privacy first. It should be open source, so we can avoid vendor lock. It's interoperable, supports multiple languages, supports non-smartphones, and it really is geared primarily for enhancing, simplifying, and amplifying the public health infrastructure using dashboards for hotspots and spread analysis. So we have many papers on our website that you can take a look at. At the end of the day, what we want to do is create a bird's eye view for governments and public health and businesses so they can choreograph the challenges faced by the COVID-19 disruptions. But if we create a bird's eye view, that can easily lead to a surveillance state if we start using digital tools. So what we also need is a bottom-up coordination amongst communities, but they should be able to coordinate with each other in a privacy-preserving way and also help the public health entities and businesses. So we think open source, nonprofit solutions like SafePaths and the algorithms and technologies we have at MIT Media Lab will, in the short run, address the public health problems. In the medium term, help us restart the economy in a safe way, and over time, also build resilient societies. Thank you.